Yeah.
Sounds like pretty much every one of my
Alright.
graduating class.
Anywho, so, welcome, hi. So, tonight,
We'll just work at dispensaries, and guess where they all work? Dispensaries.
so we're going to be doing gamma function a little bit tonight and the exponential function tonight.
Sweet.
And we'll talk a little bit about transformations tonight. Transformations should seem very straightforward to you because literally you've done them both in Calc 2 and in Calc 4. When you did U substitutions, you did the U. And in Calc 4, you did the Jacobian. Okay? That is something you're going to have to do. When you do this, you're going to be trading out. Remember, in Calc 4, we trade out like X and Y's for U's and V's. Same kind of thing. I'm going to kind of talk about it a little bit before we go home, but I'm not going to probably get into it too much tonight. I'm probably going to talk about, I'm probably going to introduce that, and I'm going to introduce the moment generating function both tonight a little bit in terms of like big picture ideas of them. But I'll do them in a video so that we can have more examples and you can go back over them 87 times or whatever. Mostly because, yeah. So Monday I spent 9 hours grading papers straight, which is awesome. And I almost got caught up. I just had to do some more on Tuesday. Now I'm caught up. Anyway. So, yeah, I don't know. Didn't get as much time to prepare this particular lesson because this is one that I don't get to teach very often, so it's not something I have ready, so it's not as in-depth necessarily as I wanted to do. That's how life goes sometimes.
What were you grading?
Well, let's see. Online tests, online homework, online quizzes, financial project things I had coming in from one class. I had calc tests, physics tests, stats tests from the high school, plus a stack of late crap. Here we turn some crap into last minute homeworks. Otherwise, I might not graduate. Although, this one poor girl, if I had to grade her papers at 9 o'clock, I probably wouldn't have been anything to say anything about it. But I got to her papers about 4:30, and I was just not in the mood. Hey, you should do a better job of cheating. Do I really look this stupid? She was writing comments like this all over her papers. Yeah. Sometimes I get a little chippy. What are you going to do? All right. So the gamma function, or the gamma distribution, if you will. The gamma function is the gamma distribution. Well, I will say them back and forth one way or the other. If I say gamma function, I really mean gamma PDF, which is basically this distribution, whatever. When I look at that guy there, that and then the special case of the exponential. The exponential is a special case of the gamma distribution. Okay? And it's kind of cool. There's some really interesting properties to them. The exponential in particular is pretty cool because it has to do with like wait times. So like how long are you going to wait for something? Given that I've waited this long, how long is it going to be before the next occurrence comes along? It has to do with the idea that these two guys are very much tied to a Poisson distribution. Okay, so Poisson, we expect a certain amount of things per time or per stretch of like potholes per road. So that's that idea that okay, well I've gone this far or I've gone this amount of time or whatever. Now what's the probability that I should be expecting to see another one come along? Okay. And obviously, there's going to be a larger pile of probability earlier on. The further out you go, it's less likely that I'm going to go this long without seeing another pothole or whatever. Okay, if I'm driving down the street. The exponential one is kind of cool because the exponential one specifically looks like this guy. It looks something along, give or take, along this line. Okay, that is, it starts high and it kind of decreases down in probability as you go. That's kind of sort of what this, but we'll talk about that, but that is what the exponential equation looks like. The gamma distribution has a little different parameters. So we're going to talk about both of these tonight. The gamma distribution, I was thinking about this today. How cool would it be to go back, I could just stop right there. How cool would it be to go back when I was farming, okay? And actually keep track of some stuff that happened on the farm. And knowing what I know now about statistics, running a lot of statistics tests, how cool would that have been, right? Besides the hogs and everything else, and rate of gains and all that good stuff, that would have been cool to see. How cool would it be to actually track like how many hours you go between breakdowns on a piece of machinery, okay? or given we've made it this long, what's probably we made it some on further, right? Or what's probably we get it within the next however often. These are the kind of things that these two functions will describe. Okay, this idea of breakdowns. As you well know, there are days when for no apparent reason you're going to get like 3 or 4 breakdowns in a row, 3 or 4 days in a row. Or are you effing kidding me? Here we go again. And then you can run it off for 2 weeks in a row, and you're just like, wait, nothing happened. Isn't that great? As you know, that's what averages are all about. Okay, we average 1 breakdown every 4 days, and we had 5 today. Okay, that's it's not that of course can be described because of Murphy's law, of course. All right, but there's no describing that other than that. That's just how life goes. Okay, as you well know, it's completely independent of whether you're in a hurry or not, or whether you have places to go, people to see, or whatever. But that's of course, as you know, that's when it's going to happen, and when you can least afford it. Although I will say the other day I had where on the Bronco where the heater hose comes out of the water pump, and it's got this weird bend in it. It's a molded special piece, and then they designed it that way. Then you put in this 2-ended hose barb, and then you bolt on another piece of heater hose that goes to the thing. It was designed that way by Ford. Stupid, but whatever. The other day I come out of Walmart, and I did not drive my pickup to town. I drove my pickup to town, not my car. So whatever, because it could happen on the way to town. It happened on the way to Walmart. Okay, when I get into Walmart, I come out of Walmart, there's water dripping all over the ground. I'm like, great. So I pulled it up. The little plastic doodad just broke in the heater hose. There's water gushing everywhere. This is fabulous. So I hoofed it home. Now, it could have been worse. So I'm learning to try to be, thankful that I didn't have to walk, that it did not get hot. There's a lot of things like this, but how these things go, especially with breakdowns. But again, I would like to go back. It would have been cool to go back and keep an eye on that. I remember there were days when you literally could not go around without having to break down the field. Just like, I didn't even get around the field one time, and we're broken down again. Here we go. And then there are other days when you're like, look at that. I went in 5 days in a row with this antique piece of crap machinery they were driving, and nothing happened. It just went perfect. Okay. So it's that idea of those kind of things, the idea of waiting for wait time. Exponential specifically will look like this guy. The gamma, we're going to take a look at some of his shapes later on tonight. This one is actually defined by 2 parameters.
So exponential and gamma are 2 different.
The exponential is a special case of the gamma. Correct. It is defined by alpha and beta.
I thought it was the other way around.
What's that?
Yeah, I'm just saying, I thought it was the other way around.
No, you're wrong. Exponential is a special case of gamma. Just fact. Sorry, you can read it. It's right there. You're good. You're good. Sorry. Yeah. So there it is. It's defined by alpha and beta. If you're looking for it in your calculator, it's not there. Well, can we look at some graphs? Yes, I'm going to do that in a few minutes. It's going to be exciting. Okay? Now, turns out that the exponential is just this guy, where alpha is forced to be equal to 1. Okay? So in the special case where alpha is 1, then you have an exponential function. Okay? That's the special case that you get the exponential. We'll look at both of these in just a minute. There they are. Now, in general, the function looks like this guy here. The gamma function. Oops, yeah, gamma of alpha. There you go. What's the matter? You good?
No, I have your exact words in my notes.
What'd you write?
No, it's
Oh, you're wrong?
Distribution is a special case of distribution. Yeah.
Cool. There is the gamma function, and you're like, okay, guess so. So gamma.
Oh, okay.
That's gamma. Looks like an upside down L. I just draw it with an R with just a right angle R is what I draw. But you do you. Okay? Yep, that's the gamma function. So gamma of alpha is defined to be this thing here. Well, wait a minute now. Cool, I guess. So then, well, what happens to this guy? Well, when you look at this, if you think about this right here, what is this bit right here? So this is x to the alpha minus 1. Okay, great. So if I plug in a value, then I'm going to get this x times x to the whatever power times e to the x, which of course you can integrate this thing pretty easily, yes? I mean, after you integration by parts. A bunch of times though, right?
Yeah.
That's gross. I'm not sure I want to do that. Do you? I don't think so either. So it turns out there's another way to parameterize it, and it's down at the bottom of the page there. It's gamma of alpha that's an alpha in case you're wondering, not an infinity, is equal to, and then it's alpha minus 1 times
Gamma of alpha minus 1.
Yep.
Is that the same thing?
That's what that means. So this right here can be also rewritten as this guy right here. You're like, okay, I guess, whatever.
No, the minus 1, is that going to be times gamma?
So it's alpha minus 1, thank you, times gamma of alpha minus 1, thank you. There you go.
Okay, so that's...
Sorry. Yep. Now we're going to do a couple examples of these, but that's how you can parameterize it. You're like, okay, well, I guess. So then, well, what does that look like to us then? Well, then, if this were true, then I need to know what this fella is, yes?
Yes.
What would that guy be? Would be equal to?
Alpha minus 2.
There you go. Like, this is just going to suck. It's not as bad as you think. It's not as bad as you think. Now, we'll go one more just for a good time.
This is not a good time for me already.
It's not as bad as it looks, I promise.
Just think of Jesus fish and draw an
Yeah,
alpha.
and they're at like a different angle each time.
Is it my problem or your problem?
I think it's everyone's problem.
Is it my problem? I mean, am I doing it bad up here?
Can
Am I
you scroll
okay?
up a little?
Am I okay? Okay.
Just think of an X.
Thank you.
Like what happened here? It's just like,
I'm just telling you. So, when that happens, so I'm not a big Greek letter writing fella, so I apologize right now. Sorry. Okay? But think about this. Let's put these guys together. Okay? So if I want gamma of, let's say, I don't know, gamma of 3, let's say. Okay? Well, that would be then gamma of 2. Oops, I'm sorry. Dang it. 2 times gamma of 3 minus 1, which is 2, of course. Okay? Now, down here, then, I need to know what is gamma of 2. Well, gamma of 2 is 1 gamma of 1. Like that. Okay? Now, of course, I can't go any further because it has to be greater than 0, yes? Okay? So then the answer then is simply this. Well, you're going to take 2, that's this guy right here, times this guy, which is this bit right here. I wish I knew what gamma of 1 was. What do you think would happen if you had gamma of 1? Oh. I made one little boo-boo. Fix this now, right now. I just saw it. I didn't see it until just now. That needs to be e to the negative x. Otherwise, that function will not converge when you integrate it. So I apologize. Thank you for catching me.
If it's gamma of 1, then 1 minus 1 is 0, so x becomes
1, and then it's the integral of e to the x,
negative x.
e to the negative x, from 0 to infinity, which becomes what? Wait for it. It becomes it becomes negative e to the negative x from 0 to infinity, which is the limit as x goes to infinity of negative e to the negative x minus a minus e to the 0, which is just 1. This, of course, is a goose egg. Yay! Wait, that means that gamma of 1 is equal to 1. So I get 2 times 1, times 1. Okay? Now, wait a minute. What if it had been gamma of 4? What would have happened? Or gamma of 5? Or gamma of anything? Well, for instance, suppose you had gamma of 7. What would you end up with here? You'd end up with 6 times 5 times 4 times 3 times 2 times 1. Yes?
Is this a dang factorial?
It is a dang factorial.
It's like a circular proportion.
It's a dang factorial. So gamma of alpha is equal to alpha minus 1 factorial.
Oh my
And
gosh.
so alphas are restricted to whole numbers?
No,
Okay.
that's gross though. Yeah.
Right.
Yeah. No, you're not wrong. So like gamma of a half turns out to be pi, or square root of pi, or something weird. Okay. I think I'll go over that a little bit more in the video.
And that's called math.
Yeah. So it's kind of fun, kind of easy to do, not too terribly difficult. So there's that. So here are some properties. So property number 1 is gamma of alpha is equal to alpha minus 1 factorial when alpha is what? Alpha is an integer. Specifically, your book points out that it's a positive integer. Well, duh. We already restricted a to be positive, right? So a positive integer. Okay? That's number 1. Fact number 1. Fact number 2 or something right in there somewhere, we already showed it. And that is that gamma of 1 is 1 by definition. We worked through it here. You can see how that popped out pretty handily. Okay? And then the third thing that they mention is that gamma of a half is equal to pi, which I will attempt. Is it square root of pi or just pi?
It says square root.
It's square root of pi. Thank you, square root of pi. I'll attempt to show you that this week in the video. I think I'll go through that just for a good time. But they all come from this particular function. Okay? Question.
What is alpha? What is gamma?
Oh yeah, I'm going to that. Okay, so gamma is the actual function. Alpha is just a parameter. Okay? And beta is another parameter. So you tell me what alpha and beta are, I use to find the gamma function for that particular thing. Okay? So just like when I say to you, the average women in America is 66 inches and a standard deviation of 2, I have just defined that parameterized their population. Okay? I can define a gamma distribution the same way. So it's a gamma distribution with alpha equal this, beta equal that. It's not as easy to see because when I say that the average woman is 66 inches tall, you're like, huh? But when you think about it in terms of gamma, you're like, I don't know what this gamma thing is all about, but you say to me, hey, this x value is distributed with a gamma distribution, with an alpha parameter of this and a beta parameter of this, bam, off we go. Okay, it's no different than that. It's no different than we said the Poisson distribution was defined entirely by mu or lambda, whichever you want to talk about it as. You tell me that, then I know what's going on. That's all I need to know. Talk about binomial NP, those two things is all I need to know. Bam, I'm off to the races. So just like those, it's just two different parameters that you have to define in order to know what's going on. Yeah?
Where is beta in the equation? Because we haven't seen anything with that.
Yeah. So, what? Excuse me, I'm going to die here. Okay? Yes. So, let me get to that a little bit more here. So, in this particular situation here, this is one that will show up that'll be a little more like what you'll actually see is when you end up having this deal here. So you'll notice that right here on this problem we had gamma of alpha like this, and this was a particular function, 0 to infinity, and this is the one I just had up here, so you don't have to write it again, alpha minus 1 e to the negative x dx. Okay. What if I told you this was your function? What if I told you it was 1 over instead? So in other words, this is strictly our gamma function. What if I said I had some function f of x that was equal to 1 over beta times alpha, gamma of alpha, right, x to the alpha minus 1 e to the negative x over b. Okay? Okay. It is of the format right now of a gamma function, yes? It is of that format. So when I look at this situation, if you're thinking, all right, well, that's pretty neat, I guess. When I look at this deal here, specifically, this is, well, if you look out here, these are just all big fat constants, yes?
Wait, so
This is a constant.
Wait, what's
This is
beta? What?
just stick with me for a minute, pal. We'll get you.
I just want to know
We'll
what
get
those
you
ones
there.
are.
Beta, alpha, beta, alpha, beta, alpha. Okay? So suppose I said to you this was my function. My stuff was distributed according to this function right here. Notice that it has the form of a gamma function right here. Do you see it? It has the form of a gamma function. But what's different? I've changed this by dividing through by beta right here. This is where your beta is going to show up always, right here. Okay? It's always going to be, well, it's going to be whatever e to the negative x over beta is. So in other words, up here in this particular case, my beta was what? It was 1. Okay? In this particular case. Okay? All this garbage out here is just a big fat constant. You tell me what alpha and beta are, I will tell you what this constant is. Okay? Now, by the way, you tell me what alpha and beta are, this sucker had better integrate to 1 over its entire region, yes? Otherwise, it's not really a PDF, is it?
Nope.
Okay? So that better be a true statement. But again, as soon as I tell you what alpha and beta are, we evaluate them, we get numbers here, so like 1/7 or whatever it happens to be, This is e to the or x to the whatever and e to the whatever. I can integrate this thing over any value. Bam, I'm done. I'm home free. Okay? So let's just pick a couple numbers for this guy just for fun. Just because I feel like it on this one, let's just let alpha equal 2, I guess, for a good time. And let's let beta equal 3, I guess, because why not? Okay? Let's just see what happens. If this is true, where x is strictly positive, okay, what does this function become? Well, it becomes 1 over beta times alpha, that's 6.
Yeah.
Now what is gamma of 2?
2.
It's 2. So this is just 1/12. And then this is x to the first power, and then e to the negative x over 3. Okay? In other words, that would be my function. That's what it would simplify down to if I started with this particular function, which they said I did. If this is what we're starting with, then I plug in the alphas and betas that I'm given. Okay? And then if I integrate it across its entire region, it better integrate to 1, number 1. Number 2, if I integrate from here to here, I find the probability that x is less than some value, or x is greater than some value, or x is between some value. Yes?
Okay.
Okay, just like we did before, yes.
I'm confused. Isn't the value, didn't you say up above one of the special rules is the value of beta, or
Alpha. If alpha equals 1, then it's an exponential.
oh, no, with the, it's always the factorial of
Mhm.
alpha minus 1.
Yeah,
In
so
this
what is
case,
1 factorial? It's just 1.
1.
So,
I'm wondering
Oh.
if we put,
good call, good call. So, yes, wait, no, but I did a beta. I wrote it wrong. Oh, no, it's of alpha. You're right. So, yes, thank you. Gamma of 2 should be 1. Thank you. Good call, good call. So this should just be 6. Thank you. I was looking at the 3, I think. Yes.
I read ahead in the book a little bit. I remember it being beta to the alpha, not beta times alpha. Is that
Beta to
something
the alpha?
different?
Is it beta to the alpha? Maybe I need to
don't
get my
know.
glasses on.
I don't really remember perfectly, but I think it might be beta to the alpha.
Oh, it is beta to the alpha. What a son of a gun. I need to get my glasses fixed. All right, let's try that again. Beta to the alpha. So it's 3 to the second power be 1/9. There we go. I can read. Good for me. Yay. All right, now let's try this thing. Let's see if this actually works. If this thing integrates like it should, and if I integrate this guy from 0 to infinity, because they said x had to be positive, it should in fact equal 1. Let's see if that's true. Okay? Now I'll bring up the old calculator. Okay. I'm not going to try to put limits on it at all. I'm just going to integrate. So, home, F3. So, 1/9 x times e to the negative x divided by 3. I get that mess right there. All right?
Mm-hmm.
Nice. So I'm going to write that down. Negative x plus 3 over 3 e to the negative x over 3. Oops. Okay? Now what happens at infinity up here? Okay? Well, take the limit as x approaches infinity. Let's see here. This is going to be 3 over 3, which is 1, of course. This is e to the 0, which is also 1. So minus a minus 1. So tell me, what happens to this beast as x goes to infinity here?
As x goes to infinity?
Yes. Here's the deal. If it doesn't go to 0, these problems.
Negative.
Listen. If it does not go to 0, you screwed up. Okay? This will always go to 0. Because, listen. If you let this go to infinity, you're like, oh my god, it's going to be infinity. Friends, where does this guy belong?
It's going to keep on
He
going.
belongs in the basement.
Mm-hmm.
So you have x over e to the x. Who wins in the race to infinity? E to the x. E to the x wins, yes? The denominator is getting bigger faster than the numerator. This thing is going to 0. You can take it to the bank. That's going to happen every time. Please, for God's sakes, don't need to sit down and like whip out and do What's his butts formula?
L'Hopital.
L'Hopital's form. We do not have to do L'Hopital's rule every time. You can wave your hands at it and say, we took calc 2. We're good. Okay? But if it does not converge to 0, you screwed up. Listen, because it's a gamma function, it will converge to 0, or an exponential. It will, because it's e to the negative x. Every single time, take it to the bank. But please do me the courtesy of showing that it's going to 0 there like this. That's swell. So here's the game. It does, in fact, equal 1. So, ta-da! Yay! It does, in fact, equal a PDF, yes? Mm-hmm. Now, what if I said to you, hey, what's the probability? What is the probability that x is less than or equal to 10 or something? Well, I don't know, but I feel like it would be something along the lines of what would be the integral of this thing, which we said was 1/9 x e to the minus x over 3 dx from 0 to 10. Okay? This is a lot of screwing around. I feel like I don't need to do this every time. Are you with me? I feel like I just did an integral. Yes? What do we call this integral right here? What do we call this thing right here if I wrote it like this instead? Could I not rewrite this as 1 minus Couldn't I rewrite it like this? And what is that guy? What's that? It's a CDF. That is exactly right. That is the CDF, yes? Isn't that beautiful after all? Now, notice that the 1 corresponds to an integral where at x equals 0 on the bottom, correct? And so this x would be the value that you're going up to, in this case, 10. Okay? This is why they came up with CDFs. You with me? This is why they did it. So here's a perfectly dandy function. You want to go from 0 to 10? Babe, drop 10 in there, you're done. That's it, you're done. But what if I want to go from 10 on up? Then you drop 10 into here, and then you do 1 minus that. Okay? So that's the game here. So listen, so this is from 0 to 10 right here. This function here is from 0 up to x. That's what this guy is. Let me write that here. Let me scoot this baby over a little bit. This guy right here is, this is the answer to the integral from 0 to x, or 0 to, yeah, let's do x, of what was my original function? 1/9. I'm going to call it p, so that if somebody walks by who has a PhD, they don't freak out and say, you use x's in both your integrals and your limits, because that would be poor on my part, and I'm not going to do that. The answer to this equation is this guy right here. Yes?
So from 10 up, it's 1 minus 1 minus that?
Okay, so let's just do this, see what happens here, okay? So if this were true, so if this is true, the way we have written it up here, we know...
Where'd you get 1/9?
It was back up the line a ways. It was 3 to the 2nd power. It was beta to the alpha.
Okay. Oh, okay.
Okay, so anyway, this is where we're at. This is what the antiderivative looked like if you evaluate it at 0 and you evaluate it at x. Okay? Now, if x is going to infinity, the whole thing ends up equaling 1, yes? So, if I put in 10, this would be the probability that x is less than or equal to 10. If I want greater than or equal to 10, whatever I get for an answer here, just take 1 minus that. Okay? That's just 1 minus it. That's it. That is why, for years and years and years and years and years, people go like, CDS, why do I have to use CDS? My calculator will give me both ends. That's true. However, this makes a lot more sense because, again, at the top end, it's infinity every time, yes, which is a big fat 0. On all these, what we call exponential class type functions, your bottom end is going to be that 1 value, which is kind of handy, okay? And so you use 1 minus that, and away you go. You're off to the races, okay? Now, notice if you graph this guy, I'm just going to go ahead and graph this just for a good time in Desmos, and we know what it should look like. We know what should happen as x goes on and on and on. Oops, this one. There you go. Give it to me. Give it to me. Why do you hate me so? There we go.
So,
Yeah, hit me.
in this example, if
1 minus.
if what the probability of x is between like 3 and 10, then our limits would be 3 and 10 on the integration. Or bound, sorry.
Well, what I was trying to tell you is that, yeah, technically you're not wrong there. Would I type something? Did I type something? Oh, because it's 3 on the bottom, you jackass. That's more better. Yay! Okay, good. So we know that at 0, how much area should have shown up at that point? None. That's literally what's saying it. Yes? And it's going to build as I come this direction to a quantity total of
One.
1. Okay? So by the time I get to 10, you can see that it's most of it, yes? Yes? Now it's not the area under this curve, it's the value of this curve when x equals 10, yes? And so a person could, and I've been teaching my kids this year at the high school to do this a lot, because I think it's kind of neat. Just put a slider in, so you just type in 10. Oops, that's 110, try again, dummy. 10. So there's an 84% chance that it's less than or equal to 10, yes? You literally just evaluate it. And of course you can type it in, nothing fancy about that. So what's the probability that it's greater than or equal to 10, or greater than or equal to 10? It's like 15%, yes, 15.5%, right? 1 minus that value, okay? It's pretty nice, it's not too bad, it's not too horrible. Now, wouldn't it be cool if there was some function out there that could give me a value of what gamma looks like? Well, yes. And GeoGebra is the only one out there that I'm aware of that's nice and free and cheap and wonderful. And this part is not wonderful. This part's kind of dumb, actually, in my opinion. And I never know which button to click on this one because the one online is just stupid. Apps, there it is. Probability. Where'd the probability one go? You effing kidding me right now? You've got to be kidding me. No, I just used it this afternoon. I said I'm going to look at it before I go, so I'm making a complete jerk of myself. Is it this one? Yeah, that's perspectives. You click on perspectives. Yay. Clearly, yes. Exactly. And then you click on probability right here. And so what you have here right now is the normal distribution, but you can select a gamma. And you can select a gamma with an alpha of, what do we say, 2? Was our alpha 2 or 3?
2.
2. Yeah, it was 3.
And 3 here.
Yep.
Okay, so that is what my actual function would look like. Wait a minute. What actual function, Jay? I don't know. Let's go look. What actual function was I meaning? Somewhere over here. My actual function was 1/9 x to the what power? Is x to the second?
No, it's
No, it's
just
x, that's right. And then e to the x negative.
Negative x over 3.
Now what are you mad about? What did I do to you this time, Betsy? Well, I really made her mad this time. There we go. Cool. Now, if a person were to zoom in on this just a skosh, and maybe change his window just a bit, and maybe go from, like, I don't know, not 0, like not from negative. Nope, that's not helpful. Yay, look at that guy. Does that look remotely like this, with the exception of, you know, if I zoomed in a little bit now. Let's zoom in a skosh more. Let's make this like, yeah, more or less. Now, I think the one on the other ones has a little more of a pronounced hump, but that's the idea of it, okay? These two things are the same basic premise. Again, this is the PDF right here. This is the PDF. The CDF is the integral, this bit up here on the first line that we did. GeoGebra has the same kind of thing. So right here, this is a probability density function. That's what this little doodad's trying to tell you. Okay? If you click over here, you can actually click on there's our CDF for it, which is the CDF we just found. Okay? And then here's the cool part. The guy can actually put in here, probably x is less than 10. And to me, I mean, God help me, I love doing a little bit of integration too. Okay. But it's kind of neat to see it has a nice, easy way to check yourself. Okay? Now, again, nothing we did with the integral was terribly difficult. The hardest part of integration, probably, since you can use 89. Back in my day, the hardest part was doing, okay, now I'm in a 500 level class, and now I get to do integration by hand, because how fun is that? Oh, and the teacher used an alpha value of like 5. So now I have, what, x to the 4th times e to some gross x power. So now I get to do integration by parts, 1, 2, 3, 4, 5 times, I think, to pull it off. And then, wait, But every single one of those, here's the trick part of that though, every single one of those guys had an x in it, yes? An x times the e to the x. Those were all going away. That's nice when x is 0, yes? They all went away. And they all go away when x is equal to infinity, yes? Or heads towards infinity, yes? Because they all have e to the negative x crap in it. So the only term that mattered was the last one, which would be cool if you could just get right to the last one, but of course you really can't get to the last one, okay? So my promise to you is I won't make you do any gross ones that are terribly awful. However, you all have access to an 89 or Desmos or whatever. No, not Desmos. You wouldn't want to use Desmos. You want to use an 89 to get a true integral, okay? I think that's kind of a big deal, and I don't care if you use Wolfram or whatever to do your integrations. It doesn't matter to me, okay? The evaluating and understanding where it's coming from is a big deal to me, okay? The concept that over here on this other page, we had this perfectly good PDF right here. This is our PDF. Well, this is our PDF. It's our PDF. And the answer to that, well, this part, no, that's not it. This part right here is our PDF. And then when I integrated it, I ended up with a CDF. That is a big concept. And that is something that when you walk away from here, I hope you can never, ever forget. Okay? You like 30 years from now, I still remember doing that. Yeah, that's huge. Okay?
Back when I was in college, I learned about PDFs and CDFs.
Yeah. So the guy who I'm taking over for in the auto shop, he's almost 20 years older than me, I guess. Anyway, today he was giving this one kid the whole charge about how back when Groom and I were kids, we had to walk uphill both ways to school. I'm like, Mike. They got it fixed when I was a kid. It was only uphill one way to school. Come on now. And so, but yes, it's 5 feet of snowdrift. It's funny to hear him say it though, because he grew up in LA. So yeah, snowdrift. That's a good trick. Good trick, Mike. All right. Now, so there's that, and it's again not terribly difficult. So the only really tricky part is given this particular situation, if alpha is this and gamma is this or beta is this, bam, what are you going to tell me about it? Okay. Now let's do a couple more examples of this. Again, not going to get hung up on the how do I determine what alpha and beta are. Let's don't worry about that too much. Okay. Right now, let's just say that I have an x. It's distributed gamma. So it's distributed according to the gamma function. The gamma function.
No, that's the CDF. When it's integrated.
And let's say alpha is, I don't know, 4, and then beta is, I don't know, 3, because I feel like it, I guess.
Okay.
Huh?
Area under versus
Okay.
value at.
So then the question is simply, well, all right, so then what happens here? Excuse me, what happens when I plug these values in? So again, here's our function. It's f of x is equal to, and then it's 1 over, and then what did it say? Beta to the alpha, gamma of alpha, x to the alpha minus 1, beta, no, e to the minus x over beta. Yes? And then we're off to the races. Okay? Let's plug this thing in. And so it's 3 to the 4th power is 81. I think. Check my math on that. Does it feel good to you? Should feel good. I feel good about that. That's 3 factorial is 3 times 2 times 1 is 6. You should check me, but I feel good. And then e to the negative x over 3. So is that 486? 486. I'm a firm believer that one should probably always double check one's self to make sure that one didn't screw something up. So when I'm doing one of these situations, I'm going to want to find the antiderivative anyways. Okay, I'm just always going to want to find the antiderivative every time. So I am just going to, right off the bat, check myself. I'm not going to plug these values in. I'm just going to find the antiderivative and see what it looks like. I need it anyways, so I'm just going to go get it. So it's always going to be a step to do here. If you're not integrating, you're doing it wrong.
So, when do you use the gamma function and when do you use the distributed gamma?
The exponential.
Well, we learned the gamma function, but then we learned this is the distributed gamma, right?
So, again, no. I said to you this function is distributed gamma. Okay, so in other words, heights are distributed normally, Okay, children, the genders of your children in your family are distributed binomially. So we're saying that this particular x value, whatever it is, follows the gamma distribution. That's all we're saying.
Oh, okay. What's the name of the function that's the x to the a minus 1 over b to the beta to the alpha times?
That's the gamma function.
That's the gamma function doesn't have a beta in it.
No, the original one didn't. The original one I drew up there was not the perfect one. That was just the gamma function. There's a gamma function without the betas involved in it, okay?
That's
So if you
with
look
beta
across the
equals
page,
1.
the gamma distribution across the page, that was with beta equals 1 over there. Across the page is what we're looking at, okay? The first one I put up there, I did value up a little bit. I had beta equals 1 the first time. The first one I drew up there was with beta equals 1. Go
But
fix your
you
notes.
used alphas in
I did. I left alphas in there, but I said let's let beta equal 1.
Okay.
You're right. You're exactly right, sir. 100%. You're not wrong.
Yeah,
Good
this
job.
has the full equation where both are
Okay.
varied.
Now, there is my antiderivative. It is a mess, yes? It is gross.
Yummy.
Everybody have that written down so I can copy it? Yes. All right, so it's negative, so it's x cubed plus 9x squared. I don't know, what else did it say? Plus 54x plus 162 divided by 162 e to the negative x over 3, yes?
Beautiful.
And I want to go from 0 to infinity. Okay? That's what you would have gotten had you done integration by parts. That's what you would have ended up if you didn't screw up. All right? You wouldn't have had it all over 162. This is somebody who's gone and gotten us a nice common denominator, and isn't that nice of them? Right? So here's the game. What happens to this guy? What is the limit of this beast as x goes to infinity?
As x goes to infinity is infinity, but then as e to the negative x over 3.
This garbage here is really in the basement, yes?
Yep.
And so you have x cubed over e to the negative infinity. Listen, e wins every time. It's getting huge way faster than the x cubed, yes? The whole thing is going to 0 again. So the limit of this mess as x goes to infinity is equal to 0. It's going to be minus. And then if you plug 0 into here, this is going to be 0, 0, 0, 162. So it's going to be negative 162 over 162. And then e to the 0, which of course is 1. And so what do you end up with? You end up with 1. You end up with 0 minus a minus 1, which is 1. So yay, number 1, yay. Good for us, okay? That's number 1. So I double checked that in fact I'm right, yay, life is sweet then, okay? So then I always do that just to make sure I'm on the right track. To me that's just a good thing to do because I needed this thing anyways, yes? So let's look at the CDF for this guy. So if I looked at the CDF for this thing, the CDF is going to be equal to what? It's going to be equal to 1 minus this bit. Remember, this is equal to the integral of 1 over 486 p to the 3 e to the negative p over 3 dp from 0 to x. That's what that equals. Okay? That's just another way of saying it. I'm going to keep writing it this way so it's clear in your mind. So then if a person wanted to know, well, I want the integral from 0 to 5, you literally just replace these guys with 5s and you're done. Okay? And if you wanted to go from 5 up, you would still plug a 5 into here, and then you subtract 1 from it, right? Okay? Does that make sense? Now Kyle says, Jay, this is a good question, Kyle. Kyle says, well, what if I want to go from 5 to 7? It's a great question. Could I just change these back to 5 to 7s? Yes! Could I plug 7 into here, get an answer, and plug 5 into here and get an answer, and then minus them?
Maybe.
Yes! Lots of ways to skin that cat, okay? Lots of ways to get there. Just get here, okay? I personally kind of dig the idea of the PDF, okay, because it's kind of a big deal. Yeah?
Dumb question. With the 1 minus the thing, is that finding, that's the normal CDF. right?
It's not the normal CDF, it's just a CDF. It's the gamma CDF. Not a normal CDF, because a normal CDF is doing the same thing, but for a normal distribution.
Oh, no, I mean, in terms of whenever we found a CDF, it was always x is less than or equal to
Always,
a
always,
number.
always,
That's
always.
the opposite
But no,
of it, right?
no, graph this thing. When x equals 0, this equals 1. Yes? And 1 minus 1 is what? 0. This thing starts out at 0, and as x gets bigger, this builds.
Gotcha.
Okay? Again, I like to see, actually, well, I'll graph this in a second, and you'll see it. You're like, oh my God. But listen, plug in your values. This is how we got the 1, was when x is equal to 0, yes? So I plug it in there, lo and behold, 0, 162, that's 0, 0, it's 1, 1 over 1, 1 minus 1 is 0.
Yeah, I'm just trying to figure out, because
It looks weird.
It does.
That's how it goes, friend.
Okay.
Because this piece here is tending to what? This piece here is going to 0 as x goes to infinity,
I'm
yes?
thinking
Which
the
means the whole
binomial
thing is headed towards 1.
ones.
Yeah.
So if you're doing the x is greater than equal to 5, you would do 1 minus that evaluated at 5, and then do another 1 minus all that.
No, you're getting too many steps in there. Okay, let's try that. Let's do that. So you want to do x is greater than 5. That's what you want to do.
Yeah.
Well, by God, let's do it, sir. What is the probability that x is greater than 5? Well, I don't know. But what I'm going to do is I'm going to use my CDF. I'm going to evaluate it at 5. Okay? What does that really mean? This is the probability that x is less than or equal to 5. Okay? Yes? Got it? Cool. Now, that's nice. That's wonderful. But that doesn't really, these are not equal. So what I can do is I do 1 minus this guy.
Yeah.
And there it is. Okay? Now, interesting that you mentioned that. Because if you look at this thing, what if I took 1 minus this guy? What would you get? If you took 1 minus this whole shebang up here, if you did this, if I did 1, I'll just put them right here and right here. If I did 1 minus that, well, if you distribute the negatives, right, the 1s cancel out, and you get the positive value of just this bit right here, yes? Which is a little awkward and weird off-putting, I think, to look at, but that's what it is. And so what happens when you put 5 into this guy? Let's find out. So I have it on my, I have this guy right here, so what I'm going to do is I'm just going to grab it such that x equals 5, give it the old approximate value, and so you'll see that at 5 it is negative. What just happened to my thing there?
You have a negative in front of you.
Oh, I forgot. That's embarrassing. That is embarrassing. That is just embarrassing. Do I have a negative in front of it? No, I do have a negative in front of it. Here's the problem, though. Okay, so yes, plus 1. Right? 1 plus that. Because what happened here, all I had was this bit here. You with me? Mm-hmm. I just had that bit right there. I didn't put the 1 in front of it. That's a little embarrassing. Let's start over. Let's try that again. Let's actually put 1 minus parentheses. Let's go grab this guy like so. So there's, oh shoot. Okay, let's try it again. Yay! Okay, so there's my CDF. There it is. Isn't that great? Oh, now. It's not right still. 1 plus. I swear I know what I'm doing. I swear I know what I'm doing. Okay, there's that. Yay me. So there it is. So that's my function. You with me? Mm-hmm. That's what it's supposed to be. I swear it's right this time.
Yeah, that's right.
It's right this time, I promise.
I thought you got the negative and then you're pushing.
I put a plus. So I just did the minus a minute ago and it was wrong. Because I want it to be 1 minus the deal, yes? But it's already negative, so I did a plus.
Yes.
You're freaking me out. Okay, now. I'm just going to go such that x equals 5, and it should be about 9%. No, I lied. It's about 8 point. Is that 8 point something? 8 point.
That's 8.8.
Yeah, it's like 8.8%. Are those 8s or 0s?
I'm gonna say. I'm gonna make a bet. I'm gonna say it's 8.8%.
It's 8.8.
Yeah, 8.8%. Phew. Okay. Yeah, me either. The only reason I figured it was that because a minute ago it was 91 point something percent, and I was just doing the math backwards in my head. Okay. So then, if I wanted to do 1 minus that, I will get 91%. There's a 5%, so in other words, there's an 8% chance that it's less than 5.
Yep.
That means the rest of it is greater than 5, yes? So roughly 91.2% or something, yes? Give or take, okay?
Sort of what I was asking is, our CDF is sort of backwards from the other CDFs that we've dealt with, don't have a one minus.
I understand what you're saying now. Yeah, I guess you can think of it that way. But not really backwards in fact that they start at 0 and build up.
Yeah.
They just look different.
Yeah, because of the way they build up.
You're just judging them because they look
I
different.
am, yes.
So-
Entirely.
Our gamma's, when it's at 0, it will be 1 if it's the CDF. Right?
Yeah.
Yeah? So that's why we're doing 1 minus, but in an actual CDF, when it's 0, it's 0, but when it's
It
1.
is 0. It's still 0. When you plug in the value of 0 into our PDF, it still comes out to be 0. I promise you.
Okay.
Because this is 1. 1 minus 1 is 0.
Mhm.
So when you plug into 0, you will get a value, a p-value of 0. There's nothing there. But by
Oh,
the time
never
you start. But to get to that, you had to put the 1 in front of it to get to that value. Because otherwise it'd come out to be negative, and that'd be weird.
Yeah.
And off-putting. It'd be -1 or something.
Okay.
And that'd be weird. We need to start at 0. Okay? Yeah.
So got a little confusing with the typos there. I just want to make sure I got this down right. So 1 minus the probability of x is less than or equal to 5 is 1 minus
The
all of
CDF.
that. So it's 1 minus 1 minus.
Right. Right.
Okay.
Right. I showed that a minute ago, then I erased it. You're right. Exactly right. Well done, sir.
So why would?
Another way of writing it, by the way, would be this. Another way of writing it would be this. We said that the limit as x approaches infinity was equal to 0, yes? So if you were to take and integrate our function, whatever it is, from x to infinity, okay, it would be 0 minus a minus, and then it would be that function that we just had. Well, it would be minus, and then it was our negative function we just had over 162 e to the negative x over 3, right? Right? And so when you did this, you would literally just get this guy right here, which is what you get when you do 1 minus that deal, okay? But I don't like to teach it that way. I mean, it's cool if you want to see it that way. I like to show it that way because, again, the idea of a CDF is builds from 0 on up,
Right.
okay? But you're exactly right. That's what it would come out to be.
Gotcha.
Mhm.
Okay.
What I'm having a hard time with.
What are you having a
is-
hard time
is
with?
that I understand this, but relating this to like one of the word problems that you're asking, that's what I'm having a really
I'm going to do some of this later.
time with.
I'm going to do some later. I'll get you. Got you. Anyway, so as Kyle was saying a minute ago, he was saying something to the effect of, hey, I want to integrate it from like 5 to 7, right? Now, again, you could do the 2 PDF values and minus them. Or you could come up here to wherever I did the integral a minute ago, somewhere up here. Is that him? I think this is him right here, yes. Is that it? Yeah, that's it, yes. Comma, if you wanted to go from 5 to 7, just a straight old integration should work just hunky-dory. And so I get about 12% chance that it's between 5 and 7. Okay? Now, that's fine to do the integrals that way, okay? But we could have also used our CDF value. So our CDF is this guy right here, yes? So I could have done this such that x equals 7. I'll jot this down somewhere. Oh, no, I won't. That's gross. So about 20.7%.
Minus 8.8.
To do it again at 5%. And so if you do this guy minus this one, there you go. Alright, so it's totally up to you.
The beautiful circle of math.
Isn't it nice? It's nice when it works. When it's kicking your butt, it's not very fun. Oh, okay.
Well,
Been there, done that.
it's like working on a tractor.
So
Except for the tractor, you can wail on the track. Book, it just seems silly. My dad told me that. We were working on a tractor one time back in the day when I was going to be a teacher, and I smashed my hand and I beat the daylights out of the tractor tracks. He goes, you realize you can't beat the kids, right? Yes, old man, I realize that. You have any patience? I'm like, yeah. And it takes one to know one, old timer. So yes, he's right. I don't. So from that standpoint, no, it's yeah, I don't know. Tractor's a little more mellow sometimes in teaching. Sometimes, not always. Now, the cool thing again is in here in this function, in this gamma function in GeoGebra, and again I'm going to go back to the actual PDF. There it is. No, I said I was. There I am. Okay, so we use, what did we say, 3 and 4? 4 and 3? 4 and, what was alpha?
4 and 3, I thought?
4 and 3?
Alpha was 4. Alpha was 4, beta was 3.
Good. Okay, now, when you look at this function right here, this guy right here, we said let's find that the value of x is less than or equal to 5. Again, they only give us the PDF, and quite honestly, that's what they should give us, 5. There it is. Hit enter. There it is. Lo and behold, there it is, 8.8%. Nice. Nice. Like, Jake, can you turn around and make it go greater than? I can't. If you click on this button right here, this button right there, I said, oh, look at that. Greater than 5.
What?
I know, right? Hey, what, this middle one, what does it mean?
Interval.
No. Let's get the interval from, I don't know, 5 to 7 maybe? Jay, you're beating the dead horse. I know. Yay, and the crowd goes wild. Yes? Nice. And of course, again, this is just the PDF, so it's shaded nicely, and isn't that wonderful? You can also click on the CDF button. And so here it actually says to you at 7, we're at 20%. Okay? And then you could put it at 5, and you'd see that it's 8%. This is less than. If you did it in between, give it to me. Come on. Oh, that's right. You can't do it between. That's right. You won't let you do in between because this is just a CDF. Okay, so by definition, less than. Okay? Again, I like this. It helps me visualize better. Okay? Back when I was a kid, I integrated, I got a deal. Is it right? I don't know. You just prayed that your answer came out to be somewhere between 0 and 1. Oh, okay. I got a probability of 12.5. Well, no, you didn't. You screwed up. No, okay. I came out to be negative. Listen, did you get a decimal? I got 0.06. Yay! Are you right? I don't care. It's a legitimate decimal. I'm going to just call it good. Okay? That always annoyed me because I like to have some other way of legitimizing my answer. Does somebody else agree with me? Okay? Does this seem reasonable when I look at it? To me, it's a nicer way to go about it.
Well, wait, why don't you just use this and call it good? Why do the work?
Come on now. Come on now. We could just all be button pushing monkeys, but if you don't understand what you're talking about, then you just look like a goob. Here's a computer calculator. Just go have fun. Well, I don't know what it means. I don't know either. Yeah. So you got to understand what's going on behind the scenes. Now, I'm a very much of a in-between kind of guy. Yes, God help me. I love technology. Of course I do. But I want to know what I'm doing with it. I don't want to sit there and go, I think. It's stupid. I want to know where I'm going. And yes, doing the antiderivatives, if it was like a race for your life, could you do an antiderivatives by partial integration by parts? Probably. Do you want to? No. You'll make a stupid mistake. Then the whole problem is wrong because you can't do an antiderivative, which, yes, in theory you can do, but...
In practice, it's
Right. So my point is, do the antiderivatives on your calculator. Go back and double check. Do the principles work? Does L'Hopital work? It better be 0 at infinity or you're screwed. If it is anything other than infinity, well, you've got a problem. You've got a serious problem. And at the lower end, it better be 1. And then it's going to just build back on up. That's how it has to be. And that's how it's always going to be. So again, do that antiderivative, get it, double check that it works for the full value from 0 to infinity, if it does. And then just evaluate it. And then if you have now your CDF, well then heck, use that. You went to all the trouble to get it. Use it. Now, by all means, check yourself. I have no problem with you checking yourself on your homework. Of course, I think you should. But to me, that's just a better way of visualizing what's happening. Okay? Again, notice that this sucker is always increasing. CDFs will always be increasing functions. Yes. The only way it can ever go down is if somewhere along the line over here, somewhere the probability of 28 was negative. That's the only way it would ever go down, right? So you'll always be building. Yes, and into 1. Exactly. Okay? Comments, concerns? All right. Now, the exponential is very similar, of course, except it's the special case where alpha equals 1. So if alpha equal 1, then you have yourself an exponential. An exponential distribution. Okay, so then what is it? What is it going to? What would it look like then?
Is the CDF exponential or is the gamma function the exponential?
Okay, every function.
Oh right, CDF. It
has
has
a
to go
CDF.
up, so then.
Every function, every distribution starts off as a PDF. When I antiderivative it, then it has its own CDF. There's normal CDFs, binomial CDFs, there's gamma CDFs, exponential CDFs. There's multiple different exponential CDFs. They're all different, but they all start at 0 and build toward positive 1 as time goes on. Okay? They are all CDFs. CDFs do not belong to just this or just this or just this. Every distribution has a PDF. Every distribution has a CDF. So when I say in the calculator I want to do a normal CDF, I'm talking about, well, I'm going to do in a normal distribution. Okay? If I'm going to use a gamma CDF, then I'm dealing with a gamma distribution. If I want to use a binomial CDF, I'm dealing with a binomial distribution. Okay? So I will always try to preface it unless I've just been, obviously we're talking about a gamma, then I say just let's go find the CDF. Well, I mean the CDF for the one I'm working on. Okay? But I'm always going to start off with a PDF. Okay? So let's just assume in this case here that our beta is, I don't know, I'm tired of 3. Let's do 4. Let's branch out. Cool. So this is beta to the alpha, so that's 4 to the first power. That's cute. Gamma of 1. What is gamma of 1? 1. Well, that's cool. And then e to the minus x over 4. Okay? By definition, this is an exponential distribution. For reasons that should be, I don't know, pretty clear, right?
The x disappeared, right, because it was
oh, I'm sorry, yes, because it'd be 1 minus 1 would be x to the 0.
0, which is 1.
Mm-hmm. I'm sorry, yes, I kind of breezed past that, my bad.
I was
Okay.
sure.
Now, we know this is supposed to be true for when x is greater than 0. So, in theory, I should be able to do this and get myself a CDF, yes? So what would it be? What would the antiderivative be here? Oh my god, I gotta do this. U equals, J, it's been a long time. I know. Well, I don't have that. I have this. Well, actually, by God, I do have that. Look at that. I do have it. There's my du. Nice. Except I have a negative du. You with me? And then this is e to the minus u. Well, it's actually e to the u, stupid. There you go. Like that. Cool. And so this is going to be negative e to the u is the antiderivative. And then just go ahead and start sticking it back in. So that's going to be negative e to the negative x over 4. Bless you. And I want to evaluate from 0 to infinity. Well, that is the limit as x approaches infinity of this guy.
Goes to 0, and then 0 goes to 1.
You're taking all my fun away. So it's 1, 0, 1. So there it is, yes? And then again, at the top end, or at the bottom end rather, I'm going to have a 1, yes? Every time. So if you think about it, in reality, what I'm going to end up with every time, if I'm doing this just from here up to some value x, then what I'm going to end up with is I'm going to end up with negative e to the negative x over 4 plus 1, or, if you prefer, and I do, this guy. And this is what we would call, because it's exponential, we'd call it an exponential CDF. Okay? And it is the probability, of course, as always, the probability that little x is less than or equal to some big value of x. In other words, it's you give me a value of x, I'm going to plug it in, I'm going to figure out what my value is. Always less than or equal to. Again, go ahead, I dare you, throw 0 in there, what happens? You get 1 minus 1 is 0. That's nice. And as x gets bigger, this piece of the e to the negative x goes to 0. And the whole thing then approaches 1. Yeah?
It's a beautiful thing.
Isn't it though? Yes, sir?
So it might be a notational thing that'll cause confusion, but the first equation you gave us, I know it didn't have a beta in it.
Because I thought beta equal 1, and I didn't say that, and I should have said that.
No, I'm wondering, even if you put beta equal to 1, don't we still have that first term being 1 over gamma to a, or gamma to alpha?
Gamma of alpha.
Which, at any value that's not 1, would make it 1 over that thing factorial, right? On the initial equation.
Yeah, but I didn't do anything with it, but you're right, yes. I didn't do anything with it, but you're right. All right, so here's this guy. Now again, notice that our original function was for the CDF, or let's go back to this deal. So it was what was it, e to the, no, it was 1/4. Was it negative or positive? Positive. E to the negative x over 4. Nice. Oh, look at that. Look at my PDF. Oh, how exciting. This is my PDF, yes? The area under the curve from here all the way to infinity, we showed is to be what? 1. Most of your probability is over here, yes?
Yep.
So if one were to graph this, one would expect to see a large hump over here, yes? And then tend to kind of down this direction, right? Well, in other words, if you were to pile up your infinity, so it would grow fast, 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 and then it would taper off, yes?
Yep.
Okay, it wouldn't come back down. It would start here, it would tend to grow up, and then kind of
Once it hits 1.
peter off. Okay? Now, so it's going to be 1 minus, and then e to the, gee, someone's awfully excited, and they tell me I yell. Okay, there it is. So if you zoom out a ways, zoom, zoom, zoom. Oh, look at that. Isn't that ugly, purple and orange? Nice.
It's like peanut butter and jelly. A
It's
little
really
bit.
not. I have actually restarted the program to change the colors, and then this one kid goes, Mr. Grimm, you know you can just change the colors. And I did not know that. It was just disturbing colors. I couldn't focus on them. I'm like, ah! I just restarted the program. And they're like, why didn't you just change them? I said, 'cause I didn't know how. And they showed me. Yeah.
And so you said these equations are specifically used for.
Specifically, this one particularly for wait times, and then the other one is more of the idea of it's the times, it's the probability that you're going to get you're going to see another Poisson thing happening in a certain time frame. We'll do some more examples of those this
Back
week
to
in the
the
video.
stupid question, 16 times a day.
Kind of like that, yeah. Yeah.
Is this being recorded?
Yeah.
So if you put words to it, this is saying that for a short amount of time, you have a pretty good chance of not having a breakdown, but as the time grows, let's say 10 days or 15 days.
Well, it's more the idea of the probability that you're going to go 10 days without a breakdown is pretty dang small.
Okay.
Probably that you go 1 day or 2 days without a breakdown, that's pretty good. 0 days without a breakdown.
So it's a
That's not
measure.
that's a big probability of happening, but it's not really particularly make you happy.
So
So in other words, so what happens to this guy? What would happen if our 4 got larger? Remember, 4 is tied very similarly to what we're going to talk about our means. But if this was 10 instead, what would happen to this guy if this was 10 instead?
It's pretty low.
So these are obviously just change these to these. Okay. So in other words, at first, right? So but our probability is it just gets stretched out, right? If you will, it just gets stretched out this way a little further. But the probability, so because you're going to say less than 5 days without a breakdown, so that's this area in here is what you'd be finding, yes? Which is right in here, it's about 40% chance of happening, okay? Probability that you'd go 10 days without a breakdown, or between breakdowns, is that idea there's about so the idea is that the probability that you would get, this would be telling you right here, it'd be telling you the probability that you'd have at least one breakdown, or you'd have a breakdown, at least one breakdown within 10 days, would be about 65% or something, okay? It'd be very strange if you did not have that, in other words, okay?
This is saying from
It's
from
wait
the start
times.
until 10
Yeah.
days from now, not I've gone 10 days.
No, it's not. Yeah, it's not saying I've gone 10 days now. That's a different kind of a distribution. Interestingly enough, probably my favorite class I ever took in college, not even second favorite, in my master's degree, a class called survival analysis. So it's very much for like people who had like big surgeries or some big heart problem or something. So given they've made it this long, what's the probability they last longer, right? So when you've pulled through a surgery, you're most likely to die in the next day or two or so after surgery, and then it drops off, yes? Interestingly enough, it also works that way for things like, you know, new alternators. If it's going to die, it's going to die right out of the box, or it's going to live a long life, a long, healthy life. Yeah, for sure. Because if there's a problem with them, you're going to discover it in the first couple of days, all right? Somebody installed something funny, like actually happened to my Bronco, I don't know, 5 or 6 years ago. Well, it was right after I got it running good, and I was commuting with it all the time, and it just died one day, and the alternator died. It was gone. Okay, fine. So I went and got a new one, put it on. I drove it like 2 days. It left me high and dry again. Well, it was bad. There was a defect when they made it. And so that's why they say when they put you know, you warranty a part, you warranty it for, you know, out a certain number of time. You're going to catch all the workmanship errors, the bad parts. You're going to catch those right off the bat because they're not going to live very long. They're going to die. You get a new one. You're ready to go. If that sucker makes it 4 or 5 years, first of all, you've got your money's worth, number one. Number two, that sucker's going to live forever. Okay? It's going to either die. And it's also true, interestingly enough, you can also talk about with kids. When kids are born, the child mortality rate, especially in developing countries, if you make it past the first couple, 3 years, you're golden. All right? Well, as far as they go. All right? Because some countries, you know, you don't live very long anyways. But it's that mortality rate when you're just, you're newborn right off the bat, right? So that first year or two, okay, that's when you're most likely to die. And then if you made it that long, then your probability of death drops off dramatically as time goes on. And then, of course, as you get older, it kind of peaks back up. But that's a little different story, okay? But yeah, it's interesting because I was like, wait, this is exactly how to do it. So I did a bunch of research on that on my own. And yeah, it's exactly right. In manufacturing, that's when it'll happen. So you either have defects in manufacturing, they'll be discovered almost immediately when you put them under load or start running them, or they'll last forever, basically. Well, until some point is that they've lived their life, okay? And or they've achieved obsolescence or whatever it happens to be, okay? And so it's kind of a cool class, but that's the idea what you're talking about. Is that, okay, given that I made this far, now it's probably I make it another day before that. That's a kind of different distribution, which we're only talking about in this class. But it's a pretty cool function, pretty cool idea.
A gamma distribution is basically something's going to happen. What is the probability that it will happen if it doesn't happen on the first day? Right? Is that what you're saying?
No, it's more the idea of it's the how long do I have to wait between them.
Okay.
Gamma's more like between them, and exponential is like, how long do I have to wait, if you will, before I get another one to show up. Okay, so I do some examples of those this week in the videos. Bring in, start off with a Poisson. So I'm going to let somebody do. I'm actually going to start off with a Poisson. Okay, here's a Poisson. It's distributed this in such a way. Now let's talk about the time frame, and we'll try to convert that over, if you will, and look at it from an exponential point of view and come at that point of view. I'm not going to guarantee the gamma is tightly wrapped to the package, but I'll try my best. Okay, yeah.
I'm wondering, so we did the alpha stretches it out over, distributing it over a longer period of time.
But why is that? Why is that, by the way, just for fun? Why does that happen that way? I'm just curious. Yeah, why is that though? But flash back to algebra 2. What are you doing here? You're doing the x over 10, right?
Oh.
So if you're doing the x over 10, what's it doing? It's stretching the function this way, right? So it's going to flatten it out, plus you multiply by 1 over 10 out front, it's going to flatten it this direction as well. Okay.
What happens, what does changing beta do?
Oh, that's a good question, right? Yeah, so this is the other reason why I love Desmos so much, and I can't really do it in Desmos. I can and I can't. I mean, it doesn't have a gamma function, but you kind of can do it in here. But I can do it in GeoGebra, kind of. So let's try it this way. So let's say, what do you want to do? 1 over, and then it's beta. So I'm just going to use b to the alpha times arrow over times, and then I have to be careful here because I think I can do factorial. I swear it's in there somewhere. Do you see it? You see factorial?
Factorial.
Ah! So then I'm going to do parentheses a minus 1 come on, get over there. No. Factorial. There you go, that should work. And then x to the
A minus 1.
So a minus 1. Oh, that's disturbing. Sorry about that. Parentheses a minus 1 e to the negative x divided by b. Cool. Make sliders for them. Interesting. So first of all, let's make these guys bigger than 0, or at least I'll just go from 1 to 10 just for fun. And do the same thing here, I guess. Yeah, whatever. So if I change this, this happens, yes? Ooh, that's kind of slinky and gross. Wow. Now, interestingly enough, okay, so you do that a bunch of times, and you're like, okay, I guess. Well, why is that going to happen? Well, so the beta only affects the constant out front, and then it affects the divide by the e to the negative x routine, okay? So this part here, obviously, when you divide by a b value, it's not going to go up as high. That second part of the function is not going to be as big, yes?
Yeah.
But when your alpha is bigger, right, then you're going to be multiplying by, like, say, x cubed, x to the 4th, x to the 5th. That part's going to get bigger, but those two are going to play off of each other different times, yeah? So that hump is going to move its way across here and shimmy around based on what those two guys are doing with one another. Eventually, e to the negative x wins, and the whole thing goes to 0, yes?
Mm-hmm.
But somewhere in the middle, that the quadratic or cubic, whatever it is winning. That's why there's a hump here. Yes? And then it drops off. What?
Where the heck did this alpha minus 1 come from?
That's
Alpha minus 1
literally-
factorial come from in the denominator?
That's gamma of a.
It's on the board.
Yeah, but I know that, but where did it come? But I mean, that's not the gamma function that you put up earlier didn't have.
No, it had gamma of alpha, and I literally just put, instead of gamma of alpha, I put alpha minus 1 factorial. Now, there's only one little issue with this, is that I should have done this in steps of 10. Are you with me? So because I didn't want to, now that's not to say that a and alpha and beta can both be decimals. Okay? The only weird part about this is it's not technically true. It's not technically true if this isn't an integer, yes? So I'm going to just make this a step. I can fix this by simply making it a step a size of 1. Oops. Step size of, I said a step size of 1.
Does it do
Other side.
integer for you then?
No, I don't know. I could just,
You put the 1 in the wrong spot.
I can't, it won't accept my thing. I know where it's supposed to go. It won't accept my inputs.
Okay.
I'm sorry.
But
I know where it's supposed to
I'm
go.
a little confused. Okay, so why did you put gamma of alpha where beta equals 1? Why did you put that in the denominator? And then you changed it to alpha minus 1 factorial, but why is it in the denominator of what's otherwise the gamma function? Or did the gamma function get more complicated when I wasn't?
So right there is the gamma distribution. He's talking about the gamma function.
I'm just trying to show you where I found it. Somewhere I put it. Maybe it's on the first page. I don't know. Whatever. There's the first one I wrote, and then over here is the second one. I think it's on the second page. It's here somewhere. It's right there. No, that's not it. It's here somewhere. Is it down here further?
No, scroll up. It's right under the box.
Gamma
Oh, it's right there. It's right there.
alpha, but oh wait, so I think
I can't see it for looking
it's
at it.
not okay, so I didn't put that in. I put the E there instead.
No, there you go. What are you going to do? What are you going to do?
Crap, it's even more complicated than
Anyway.
I imagined.
So again, this Desmos one is an approximate version because I didn't make that a step size of 1 for my A. Because technically, if it was 4.2 minus 1 factorial, that's not true. But because if A was an integer, then this would be a true statement, and I can get a pretty good approximation for it. Okay, that's probably the only ones I'm going to ever ask you about. Okay, it's nice integer ones because you're welcome and whatever. Now, if a person were to do this, however, in here, oops, right, somewhere over here, there it is. Now again, I could actually put in, you could say, well, what happens if I make B, let's go back, actually let's do this, get back to this, there you go, make B bigger, yep, make it bigger yet, yep, and it does, that thing that annoys me about this a little bit is it automatically stretches the line and scales it, so you're like, nothing happened. Yes, it did. Yes, it did. It totally did. It's there. It's weird. That's something I don't like about it. The Desmos is like, oh, I get this weird little bumpy line. It barely shows up. Good, but then you actually have to change your window so you can see it more better, whereas this does it for you and you're not really sure anything happened. Interestingly enough, what would be the expected value for these guys? We should probably jot that down. That's probably a big deal. So the expected value for any gamma function. And these are on page, if you want to refer to them for your own personal benefits. They're on page, oh, for God's sakes, where are they? They're on page, oh, where are they at? Let me tell you where they're at. So you can, oh, there they are on page 196. So the expected value is alpha times beta. And sigma, and your book writes nice sigma squared like it should, good for it, and is alpha times beta squared. All right. Well, that's great for a gamma. What about for, what's that?
Sorry.
No, that's fine. Just look at it.
It's weird.
We're going to go look at a couple examples here in a minute. You're like, oh my God, that actually makes sense. Now, what would it be for the exponential function? Well, the exponential is a special case when alpha is equal to what? So just beta, right? And, oops, is beta squared. Exactly right. Okay. Ta-da. I have a question. If you go back and look at this GeoGebra picture that I just drew up here, where does it look like, ish, where does it look like the balancing point would be for the probability on this guy? Somewhere in here-ish, maybe, give or take, but somewhere maybe in here-ish. This is shorter, but there's a lot more of it. This drags over here quite a ways. The balance point's probably going to be in here somewhere. Hey, look, 4 times 33 is 132. 132 is right in here. It's about where I would do it to split it, to balance it. That is the idea of the expected value, right? It's that idea of that's where the average would be, the balance point, if you will. That's what an average is. It's where you would balance it, yes?
Yep.
Where you put the fulcrum,
Yep.
okay? Again, don't panic that it's not right in the middle like a normal distribution. That shouldn't be in the middle because this is not nice and symmetric, is it? So it's got to have to be pulled over this direction. By the way, this kind of looks like what the price of houses would be, like say in St. Helens. Lots of lower houses, although they're not as cheap as they used to be. But compared to like Lake Oswego. But as you move this direction, there's fewer and fewer and fewer of them. It would be somewhat, we'd say it'd be skewed to the right in St. Helens because there's a big pile down there on the left. And then they'd be pulled out this way. 1 or 2 of them would pull the average this direction towards it. And obviously the picture would be bass-ackwards in, say, Lake Oswego. Very few cheapos, but a ton of them up around this end. Same basic idea. But again, just like we talked about back in the day, somewhere you talked about it, we used an average. And the average is affected by outliers. It's always pulled toward the upper value, the bigger values or the extreme values. In this case, giant values. So it's going to pull it this way. And that's where you would balance it. Okay? That's pretty cool. And then, of course, the variance would be alpha times beta squared. Beta squared is 900 and something, almost 1,000, times 4 is about 4,000. Square root of 4,000 and something is, I don't know. No, I don't know. You should use a calculator, but I don't know. But anyways, I don't know. 33 squared times 4 is, what is it? 33. 33 squared times 4 is
4356.
43. What's the square root of that?
66.
66. Okay, so the standard deviation, or the variance here would be 66, right? The variance is what you just found. Okay? And I'm sorry, the standard deviation would be 66. The variance would be that big number you found, 4,300, whatever it is. But the standard deviation would be about 66 here. Okay? Yeah, nice.
And
On this
what's the
particular problem.
percentage within a standard deviation?
Okay, well, in a normal distribution, it'd be 68. And not a normal, but in a symmetric distribution. Because this is not symmetric, see, that brings up something that we're not going to get to talk about because this class doesn't cover it. But that's interesting because then you're like, well, wait, what if my data isn't symmetrical? That's a good question. Well, it still has an average, yes? Still has some average here somewhere, some mean value here. Still has a standard deviation of some sort or another, okay? So then the question might be, well, you know, what percent would lie in here? Or what percent would be at least, can you give me a guarantee? Well, there's a fellow by the name of Chebyshev, a Russian dude. Yeah, it's mentioned in there. We just don't get to talk about it very much. It doesn't really belong in the material, but it's interesting that it brings up something to talk about right here. Okay? So he said that at least 1 minus 1 over k squared percent times 100% of the data is within k deviations of the mean. Now, this is not good, right? So it's not as good as the other one. So you're like, well, what if it was 1 deviation? Well, that'd be lousy because 1 squared is 1, 1 divided by 1 is 1, 1 minus 1 is 0. Oh, That's cool. There's at least 0% within one deviation of the mean, which is less than helpful. But you're like, what if I go 2 deviations? Well, that'd be cool. So if I did 2 deviations, it'd be 1 minus 1/4, which is 3/4 times 100, be 75%. So at least 75% would be within 2 deviations of the mean. At least that much. It's a bottom line. Now, clearly, as the more symmetric it gets, when it's perfectly symmetric, then it's actually 95%. Well, last I checked, 95 is at least 75. So it doesn't counteract that. It's just one of those deals where this is the best I can get. So Chebyshev, it's kind of a neat little, again, it's a quickie little down and dirty. I'm guaranteed at least as much as in here. But it's very down and very not. It's very dirty and it's just kind of iffy. Okay, it's interesting because it fits nicely. You're like, well, what percent? Ooh, I can't use the empirical rule. I can't use a normal distribution because it's not normal. Now what can I do with it? Okay. Now it would be really cool if I had a random number generator that could generate gamma distributions, but I don't. But if I did, hypothetically, well, that's not. I know what you're thinking, Jay. Couldn't you dummy it up? I could dummy it up, okay? But hypothetically, if I had numbers that came from a gamma distribution, let's say, I don't know, 1,000 of them, what do I know about the x bars of that sample? So here's a sample of 1,000 data points, yes? Okay? And so it came out of, let's just draw this up. I'll just draw it up. Here's a bunch of numbers. I put them into Excel, and aren't I nice? There I go. 1, 2, 3, 1,000. Good, good, good. And it came from a gamma with a mean of, with an alpha of 2 and a beta of 4. That's great. Now, if I take the x bar from this guy here, right? If I take the sample average, how do I know that it's distributed? All of the x bar, by the way, I promise this is on the test. I promise this is on the test. Central limit theorem states, and I quote, that the x bars are always distributed how? Normally, guaranteed, with the same mean as the original distribution, yes? What is the mean of this distribution? Of this gamma distribution? It'd be 2 times 4, which is, bless you, is 8. That's right. And a standard deviation over the square root of n. I know that to be a fact. Okay? So, here's the game. You're like, well, what is the standard deviation here? I don't know. But I do know that the variance is equal to 2 times 4 squared, which is 32. So, sigma is the square root of 32. So, it's the square root of 32 divided by the square root of 1,000. I guarantee you the x bars will be distributed thusly. That's what the central limit theorem states. Okay? That's just a review from last time. Last time, you recall, I generated a whole bunch of data, yes? Yeah. I did it from discretes, I did it from binomials, I did it from all that crap, didn't I? Mm-hmm. I feel like I did. And we went and checked it, yeah? And this literally is no different. I said I can't generate it, so I'm just going to pretend I did.
And
so there I did.
Because of that, we can take samples from
That's
things,
because
right?
I can take samples from anything and then make z-scores for them and find out what the probability that what I saw happen. That's exactly right. That's the whole point of the central limit theorem. It doesn't matter what you're producing. It doesn't matter what the distribution is. The x bars will always be distributed normally. Always, 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 always.
X bars is in the value.
As in the sample means. No matter today's, tomorrow's, this afternoon's, tonight's, every sample mean of size 1,000 will be distributed thusly. If it was a sample mean of a sample size 100, it would be 100 right here. 10,000, 10,000 right here. They will all be distributed thusly. Every time. Take it to the bank. Yes?
I was going to say that in DSP there's IR filters that they're like called Chebyshev or whatever.
Yeah?
Yeah.
Nice.
And that has to do with sampling.
Yeah. Because you don't know, because if you don't know what kind of distribution you're using, then you can't be assuming that it's
normal.
whether it's bell-shaped or normal or symmetrical. So then you use Chebyshev. It's good. I like it. Interestingly enough, weird stuff shows up in places you didn't expect it to show up. I think the weirdest thing I ever saw in the stats class, this guy says, okay, we need to do transformations. So I'm thinking you're going to take a log of some big numbers. Yeah, makes sense. Sure. Yeah, we do a few of those. You do this and that. Okay, sure, I'll buy that. Like you take the log of your x's and your y's. That's pretty cool. Neat. There's lots of cool things that at least literally make sense. This one day the guy goes, I know, we're going to transform our y values. We're going to take the arc sine of them. Huh? Yes. Why? It's because. Okay. Never did really have a particularly good understanding of it, like why you did that. There's one of those deals where you're just like, wait, I'm in the middle of a stats class. We're talking about some random stuff. And all of a sudden you're going to pull this arc sine out of your back pocket. Where did that come from? Okay? And it's interesting, like I've never heard of what you're talking about back there. But there, oh hey look, Chevy Chef, that's interesting. That's where it comes up. Just the weirdest little connections from time to time will pop up. And you're like, oh, it's enlightening tonight, good for me. Yeah, that's what I enjoy about this kind of stuff, right? You're in places where you didn't expect it, and then, oh, there it is. Yeah. My buddy went to Gonzaga, went to one of his classes one time. I had already graduated, he was a couple years younger than me. And I was sitting in a class with him one time while I was waiting for the wife to be done with something. It's like she was taking her accounting test or something. And we go to this class, and this guy's mumbling at the board. He faced the board the entire time, mumbling, writing from one side to the other, and then flipped it up, and then wrote from one side to the other again, for like an hour and a half.
It's fantastic.
And then walked out. And he's a Chinese guy, and he had a very thick accent, on top of the fact that he was mumbling the entire time. And I'm like, Tim, are you getting any of this? No. Just write it all down. And there wasn't Google back then, so you couldn't go home and Google it. So you had to actually read the book. It was horrible. But I was sitting there watching the guy, and I'm like, oh, look at it. I know all of this stuff he's putting up there, but I don't understand how it relates to what Tim's supposed to be learning. Okay? I understood the math that the guy was doing. No idea what electrical goofiness that he's supposed to be learning from the math that was going on. I was like, oh yeah, I don't know. My buddy's an electrical engineer. But I was just sitting there going, huh, all right. And it's funny, the best part is, he's still in debt up to his eyeballs, school loans, even though he's been out for umpteen years. And I'm like, that's awesome. So you went to college, you sat there, somebody mumbled at you, and then you had to go home and teach yourself how to do it. It was awesome. Yeah. Although I'm not sure it might.
That's pretty much electrical engineering.
Okay, so it says let's let y equal g of y rather equal this guy here. So y plus 3 over 2 times a half, which is equal to, of course, your book goes ahead and does this out for you, y plus 3 over 48. Wait, why does it say over 2? Oh, because it's over 12. Is there a squared somewhere that I can't read? My God, my eyes are getting bad. Oh yeah, so y, okay, there, I see the problem. It was y plus 3 over 2 over 12. There we go. Yay, I'm not stupid. Yay. Good. From -1, less than y, less than 7. Beautiful. Okay? And then, of course, it's 0 everywhere else. Now, why did they tell me all of this garbage? It's going to help me clean things up, I think, in a minute when I substitute. Okay? I think. I'm not sure it's going to help, but it might help. Okay? Now, let's try this. It said that's what y is. But let's say that y is equal to 2x plus 3. Okay? If y is 2x plus 3, well, I would like to have a function that talks about the distribution of x. Yes? I'd like to know something about the distribution of x. That's what I'd like to know. Okay? So first things first, that's what y is. I want to turn this baby inside out and solve for x. Okay? So if you were to do this, what would you get?
Y minus 3 divided by 2 is equal to x.
Y minus 3 divided by 2 is equal to x. Is that what you get? Something along those lines? Okay? Cool. Nice. Awesome. Okay, so first things first. If that were true then, okay, then how would that affect these guys over here? let's start with the easy stuff. Now remember, back in the day when we did Calc 2, when we did some integrations with substitutions, and let's maybe go just kind of off to the side, this little sidebar. If you were doing this back in the day, what would you do? Off to the side here, you do something like, let's let u equal 3x, right? And then you let du equal 3dx, right? And this 3 right here, I don't have one of those, so I'm going to bring it back over here, like so, yes? 1/3 du. So I'm going to have a 1/3, and then I'm going to have the sine of u du, right? And then you might recall, if you had me, I always said that I like to integrate first and then resubstitute, because that's how I like to do it. But a lot of times what a guy can do is plug this into here and into here, yes? And you transform those on the way. So it'd be 0, and it would be 3 pi over 2. In essence, that's what we're going to be doing right here. Okay? In essence, that's what we're going to be doing.
Wait, how do
We're
you
going to
get
be
3
taking
pi
our
over 2?
limits. 3 times pi over 2.
And then, wait, then you plug it into there?
What are you saying?
You plug things into weird places.
Dude, it's Calc 2, man. I don't know what to tell you. Right here, look at it. So here it is. I just found those values. Now if I integrate, instead of resubstituting 3x back in, I'm just going to plug these new values in. They're no longer x's anymore. They're now what?
U's.
They're u's. That's what we're going to do on this next page, friends. Over here we have y values, yes? We're going to run them through this guy here, and what are we going to get out of them? We're going to get x values out, yes? So -1 minus 3 is -4 divided by 2 is -2. And then 2.
Yeah.
Right? 2 and then 2? Okay? That's cool. Interestingly enough, we're going to be talking about the transformations here. Okay? So talk to me about the change in x with respect to the change in y here. In other words, let's let this happen here. So if you come over here, oops. If you come over here, well, I don't want to talk about the change in y. I want to talk about the change in x. Oh, go away. I don't care about that crap. So what would dx be here? Dx would be 1/2. Is that true? 1/2 of a dy, if you will. This is all constants, yes? So this is 1/2 y minus 3/2, yes? And the derivative is going to be 1/2 dy, right? And then, of course, that goes away. So it's this relationship. This idea right here, this little fudge factor, if you will, right here, what we refer to as a Jacobian. And we're going to get into that more in the video this week. Typically, we didn't think about that. You've heard that in Calc 4, but in Calc 4, we were replacing x and y's with u's and v's. It's the same principle. And if you recall, in Calc 4, I even said that, didn't I? I said this is just like we did it in Calc 2, but you're doing it with you're doing 2 variables, so you have to do it with the Jacobian determinant, yes? And so we'll look at that. It's going to be good times, I hope. Okay? And the idea here is that you're talking about how is y changing with respect to how x is changing. Okay? So then we're going to go back up here and we're going to edit this function up here and look at it and see how that changes, how it changes out differently. Okay? And so gotta get my glasses fixed. This is ridiculous. Now that I step back from the book and I stand over here, I can read the book clearly. I see my f of x's were actually distributed a little differently. So you can see where my y's come from. So let me rewrite my x's. This is what the answer for y is, by the way. This is what the answer is for y. But let's see where it came from, okay? This is what f of x was supposed to be. And I'm going to have to stand over here so I can read it better. It's x over 12. And then it goes from 1 to 5. So let's try this again without screwing it up this time, Jay. I know, I'm pissed too, because I'm mad. I feel like. Now, let's get rid of this guy. Let's run our 1s and 7s. Let's don't run our 1s and 7s through that. Let's run our 1s and 5s through this guy. If you run your 1 through there, what do you get? 1 minus 3 is -2. Divided by 2 is 1 minus 3 is negative. So it's a -1. Is that correct? -1? Good. -1. And if you plug 5 into there, 5 minus 3 is 2 divided by 2 should be 1. Okay? and something's still a little goofy, but we'll figure it out when I get there, okay? So something's a little screwy still, but I'm going to get there, I promise you. Now,
Why don't we just sub
Oh.
X into Y?
thank you. Let's plug these guys. Let's try it again. Let's plug these guys into here. I got to give them the right deal. Geez, I want to quit. 2 times 3 is 5, yes? Good. It's 5. Good for me. Good Lord. It doesn't matter. I will redo them tonight for you, I promise, okay? It'll make sense to you when I'm done, okay? I promise. Okay. When we're all done, let me just get down to this part down here. This is the part that's actually important part. So what I said up here was x was equal to this guy here, yes? You with me?
Okay, yes.
The x is equal to that guy right there. Okay. Now, what am I going to do? I'm going to plug it into here. Are you with me? I'm just going
I'm with
to
you.
replace the x with this guy. Yes?
Okay.
Okay. This is the part that matters. I will make it all crystal clear, I promise, tonight. Okay? Divided by 2,
Over 12.
divided by 12. But J, in the original thing, there was an extra half there. That's the Jacobian. There you go, Jay. You moron. My God, I'm an idiot. All right. And then, it's literally, we're looking for a function of y, are we not?
Do you have to stare so intensely?
Yes. And I will make sure this works out tonight when I get home, so you'll see where the 1s and the 7s come from. But again, it's just being transformed. That's all we're doing. That's it. You're like, this, so all I did was I replaced the x with what x equals in terms of the y. Yes. Okay. That's cool. But they don't change at the same rate, so I multiplied by the Jacobian. Sweet. And then I ran my x's through and I changed them into y values. This part here I will make it perfect tonight, I promise you. And I'll do these examples, not tonight, tomorrow night.
I was
I
just
post the video.
wondering, does the Jacobian doesn't have any effect on the bounds?
No.
Okay.
No, just those.
It's just the fudge factor.
Just the
make
fudge
bounds
factor.
work.
Thank you.
Gotcha.
And is this just to make the math easier?
Yes. Well, to make it easier, maybe, but to maybe make it so that where you happen to know that you have something x that makes sense, but you're going to not use x, you're going to double x and add 3 to it for whatever reason, because that's the thing that you're interested in. So you're not interested in x so much as you are this other thing y, but it's a function of x. And so instead of having to jump through all the rigmarole, you can just use this guy to get to what you actually want to know. Get a PDF for him. Okay? And it's just basically the same PDF, but altered a little bit. Okay? I will do several examples of these, and I'll do them right and perfect. I'm sorry. Now, I will say this, you might recall, or you might not, and I'm not going to do this whole problem at all, so don't even start on that. But back in Calc 4, and that's why you had to take Calc 4, if you could do something along this lines here like this. In Calc 4, you said x, let's let x equal, I don't know, u plus v, and y equals v, or whatever it is, I don't really care. And we were given some situations like this. And in Calc 4, we were done it in such a way that it made the integral easier, typically, that's why. It wasn't some random, throw these in there and make it harder. It was supposed to make it easier. Okay, that's the whole point. Okay? Now, specifically, that's what's supposed to happen. Now, in statistics, it's more like this. You've got this guy over here, okay? It's this particular distribution over here. When I put them together in some fashion, you know, like, if I recalculate them, instead of taking about 2x and 3y or whatever, let's just change them to like u plus v. Let's change them to make it easier for us to deal with it. Okay? So instead of going 2x plus 3y, we'll just say it's u plus v, or whatever it happens to be. Okay? And so that's the game. So the Jacobian, and again, you may remember this, and if you do, great. And if you don't, well, that's going to be a problem. Okay? And so the Jacobian, you got to remember this, it's kind of a big deal here, is that it's always, it's always the idea of, now you might recall this back in the day, what did we have to do with this business here? Okay, now if you recall, typically, when you're doing the sign of 3x, over here, what did you say? You let u equal 3x, yes? Mm-hmm. Right?
Yeah.
So what does that say up here? These guys have to be solved for u's and v's, yes? Mm-hmm. So let's say that I have gone ahead and done that. So that means v is equal to y, obviously, yes?
Yeah.
And so then if v is equal to y, what is u equal to?
X plus
X
y.
minus y?
X
Minus v.
plus x minus y. Yes. Yes, x minus y. Yes, thank you. U is equal to x minus y. Very good. So that's the first thing. It has to be in this format. Okay? Because just like when we were in Calc 2, we said u equals to 3x. The same thing must be true here. The u's and the v's must equal our original x's and y's. Yes, like this. Now, how does the Jacobian work? Well, in this case, it'd be du dx, du dy, dv dx, this is partial derivatives, and dv dy. And then I take the determinant of this guy. And so if it's been a while for you, the determinant is simply this one times this one minus this one times this one, yes? That's the Jacobian determinant.
So du
Okay.
dx, du dx.
So I need du dx times du dv, or dv dy, I mean, minus du dy times dv dx.
Oh, that's a du dx. Okay.
What do you think it was? They're partial derivatives.
I thought it was a dy dx.
Oh.
Okay.
Sorry. Anyway, we'll run through several examples of this on the video, okay? Notice it's not very difficult. Hey, the Jacobian came out to have an x and a y in it. Okay, cool. Go ahead and throw those in there. Does it mean that they'll always be guaranteed to be things like 1/2? No. Could they come out to be negative? No, the Jacobian's always positive, right? Don't forget that. The Jacobian is always positive.
Why?
Because it talks about a rate. It's a rate. It's a rate. So just kind of keep that in mind. It's a rate. So just be aware of that when you're doing these guys. Another reason that it has to be positive too is there's no rhyme or reason why the du and the dv had to be in this order. I could have named them just as easily the other way around. In which case those have been flipped, which means I would have got the negative or whatever I got the first time. But that's why we take the absolute value of it. Okay? So again, this will be the game. We'll be given some PDF over some region. We will then alternate it, change it in some fashion. Voila, here we go. Notice if we're dealing with a Jacobian, I'm only going to deal with this guy on a continuous PDF, right? A continuous joint PDF. I only do that one on that kind of a deal. I won't do one for you on, I might do an example, but I'm not going to make you do one, okay? So transformations, and then the last thing that we're going to do in the video this week will be the moment generating function, which some of you will find to be very, the continuous one, you'll be like, wait, I've done this before somewhere. And you have.
Is it physics?
No, it's differential equations.
Oh.
No.
Yeah. Well, if you took it with me, you did. If you took it with somebody else, maybe you didn't. I don't know. So, the moment generating function, so the moment generating function looks like this. It's the integral from negative infinity to infinity of e to the tx f of x dx. Okay? For the continuous function. Wait, what do you mean, Jay? This is similar to what we did. Well, it is similar to what we did. It's very similar to what we did when we did Laplace transforms. Yes? It's very similar, slightly different, but very similar. You'd be like, wait, we integrated from negative infinity to infinity. We did. We multiplied through by e, but remember then it was e to the negative st was the only difference here.
Yeah.
This is not going to be that way this time. That's okay. When you integrate this thing, obviously at negative infinity, what's going to happen? Well, you're going to get e to the negative infinity, yes? Presumably, this guy also has an e to the negative x in it, yes? Because if it's a continuous function that goes from negative infinity to infinity, this better have an e to the negative x in it or something, yes? Because otherwise it's not going to converge, and we're screwed, okay? So, in reality, some people might think that this is going to blow up. Don't panic, because at the negative end, this guy will kill it. This, again, obviously is going to have, in practice, going to have an e to the negative something in it, yes? Because, again, it has to converge towards infinity, okay? Which means that the positive ones, it'll also kill it dead, okay? So, in theory, that's how it's going to work. Now, what's going to happen is you're going to get some function out of this thing. It's going to be some function. What's it going to be a function of? Well, you're just going to be some function here of some parameters. Some parameters. Where the parameters will come from is they'll come from this guy here. Okay, there's some parameters that will come from this piece right in here. So for instance, I will do a couple of examples of a normal distribution and maybe a gamma or something else. I don't know, I'll run through a couple of them. When I do them, this thing, that what I get is going to be a function of this. Now, what you didn't know is this, I didn't tell you. The expected value of x is what we refer to as the first moment. The first moment. Wait, physics, torque, wait, moments, fulcrum, what? Is that why the average is always at the fulcrum? Because it balances the moments? Yeah. Yes. Now, what is the second moment? Well, the second moment is the expected value of x squared. Is there a third moment? Yes. Is that easy to find always? No. If you have a function that will tell you what the first, second, third, fourth, 18th moments are, would it be easy to find? Yes. Can I use these deals to show you, for instance, why on a mean the expected value has to be mu, why the standard deviation has to be sigma, things like that? In the discrete version of this, can I show you why it has to be NP, has to be the mean for a binomial? Yes, yes I can. And so it's kind of a cool deal, okay? So we'll look at those a little bit. Now, expected the second moment. See, again, we've already found this guy. In fact, what have we used him for? Yes, the variance is the second moment minus the square of the first moment. Nice. In fact, that's how I was taught it back in the day, which made no sense when she first stood up there and said it. I'm like, what are you talking about? How about you tell me it's the mean, the standard deviation or variance first, and then after you do that, then you surprise me and tell me I already found the second moment and the first moment. Yeah, but I don't know. She told us that like day one. First moment? Moments? What are we in physics? What are you talking about? But I don't think she had a clue that, like, the physics part of that. Some weird professors. One time this lady, well, that chick was the weirdest. But this other lady, they asked her one time, can you give us an example of where complex numbers are used? She's like, no, I don't really like application. I think it maybe has something to do with electricity, but I don't know. And I don't care. Okay, now let's do another example. And I'm like, ah! Without application, what's the point? If you were never going to use tools, why do you have a toolbox? What's the point? Is it to look like? Is it a decorative thing? Is it a talking point in your room? Are you feng shuiing your room with toolboxes? Which is a good look, by the way, but if you're never going to actually get the tools out and use them, why do you need them?
So you can take them out and look at them, and then put
Oh,
them
my
back.
precious. No, that's
You know,
weird.
like a party trick.
Appreciate it for the
Look what
No, I cannot. By the way,
Look at this hammer.
abstract algebra made no sense to me. Today we're going to talk about abelian groups. They're so cool because they have inverses and they obey the commutative property. They have commutative property. I think they have inverses too. Like, that's cool. Why? Well, it turns out it forms the backbone of all telecommunications. But would it have been that hard to tell me that? Yes, apparently. This is just stuff. By the way, it was discovered back in like the 30s or 40s on a back wall with no application at all. And it wasn't until later they're like, hey, this will work for what we're doing. That creeps the bejesus out of me. You're doing something, you're like, I need to develop math for this? Psh, cool, you built a tool. It happens all the time. I've done it myself. I need a tool, fix a tool, this tool will work.
Janitor will write something on a board, and
Right.
you're like, that's
Right.
math.
Exactly.
And you use it.
All right, so here's your quiz. 3 questions.
Yeah, she did.
Wait, what?
Sheet of paper. I literally gave you a warning that this was going to be on the test tonight, the quiz tonight. It is an easy quiz.
Okay, that's relative.
We'll see about that.
No,
You said
it's.
it was normal, but I found no video on normal.
I talked about normal in class all last week, babe. That's all we talked about in class all 3 hours last week. Normal distribution. Yes? I did.
I was there.
I know.
Prepared to be disappointed like my parents.
Okay. So listen, these NFL linemen. I don't know any. So help me God. If anybody asks me, they say I don't know what an NFL lineman is, I'm going to vomit. This is just a part of a problem. Nobody cares. It could be a BMW. It could be anything. I don't care. Their weights. Yes, the NFL lineman. I'll specify lineman. Weights. Linemen.
Thank you.
O linemen, if you want to get technical. Their weights are normally distributed They have a mean of 320 pounds, a standard deviation of 15 pounds. Cool. What percent weigh more than 300 pounds? That's question number 1. Question number 2. If you take a sample, if you select 60 linemen, what is the probability that X bar is less than or equal to 316 pounds? Nice. Cool. What weight corresponds to the lightest 10% of line men? There you go, Marie. We just talked about that before class. Nice. No, we're in another room.
Just open book or no?
In another room?
All right, you can look at your notes, sure. Yeah, how about it? Sure. Sure. If you know what you're doing, it's like 5 minutes and you go away. If it takes you 20 minutes and you're doing okay, it's fine. Just think about it a little bit. Seriously, think about it a little bit. We did examples of all 3 of these last time. Matter of fact, I talked in length about this one because I talked about, like, in education, you want the smartest and the not smartest and whatever. You can use Excel, you can use your 83, 89s, 80 whatevers, I don't care, have at it. Your instincts. You do you.
My instincts?
Good feeling.
That's a good one. All right, what do you need, man?
I need a sharpener.
I don't.